In this video, I'm going to describe a model, an ODE model for the change in genotype frequencies in a population. And I'll set it up in such a way that it allows for differential survival of the different genotypes so that we can think about the influence of natural selection. So I'm going to define P1 to be the number of individuals with a genotype AA. P2 will be the number of individuals with genotype AB, and P3 will be equal to the number of individuals with genotype BB. And you'll notice that we can add these up and get the whole population size. And what we're interested in is not so much the whole population size, but which of the three will end up dominating depending on which one has a selective advantage and how they evolve to take over a population, if they do. Okay, so let's just write down a general expression for P1 prime. So how do new AA genotypes appear in the population? Well, I'm going to make the assumption that all of these three genotypes, these types of individuals, will all reproduce at the same rate with a birth rate B, a rate constant B, but their deaths will differ. So let's just write down a single B for all of them. And now we have to multiply by, well, first of all, we have to know the total population size, and we'll multiply that by the expression I'm going to put in these square brackets. And this expression is how often you see AAs appearing. So that'll depend on your probability of mom being an A and dad being mom being an AA and dad being an AA, for example. And then you want to add to that the probability of mom being an AA and dad being an AB. And you'll notice in this case, the children, all children of this pair will be, for sure, will be little a, because that's all mom and dad have to give. Mom will definitely give an A, but dad has a 50-50 chance of giving an A. So this will only be half the time result in AA offspring. And then we have another scenario of the similar type, which is mom is the AB and dad is the AA. And finally, 1/4 of the time, we'll have mom being an AA, 1/4 of the time when mom is an AB and dad is an AB, only 1/4 of those offspring will be AAs, and so we multiply that by 1/4. So that gives us the frequency or the chance of an offspring from the population being AA. And then we multiply that by the total population size, and the B in front of that gives us our overall birth rate. And then we have a death rate, so we're going to subtract off, and population 1, which is the AA genotype, will die at a rate D1 multiplied by its population size. And now we can write down what that is. So B will be now the probability of mom being an AA and dad being an AA. Well, we know that P1 is the total number of individuals with genotype AA, and P is the total population size. So we can write down the probability that mom's an AA. Well, we just have to get lucky in our choice, and that probability is going to be exactly the number of AAs divided by the total population. So we have a P1 over P, and then dad, same probability, P1 over P. And then we add to that. Now you'll notice the next two, this one here and this one here, there's no difference really between, statistically speaking, there's no difference between mom being an AB and dad being an AA, or mom being an AA and dad being an AB, because we're assuming that they're uniformly distributed throughout the population. And so we're going to get a half plus a half gives me 1, and then we'll have a P1 over P times P2 over P for those frequencies. And then we're going to add 1/4 times P2 over P multiplied by P2 over P. And all that gets multiplied by P and minus D1 P1. So we can simplify that down a little bit. And I'm actually going to not cancel those P's because we're going to use those later. I guess it doesn't really matter, but we have P1 squared, B times P1 squared plus P1 P2 plus 1/4 P2 squared, all divided by, well, multiplied by P and all divided by P squared. And then minus D1 times P1. Now we can go through a similar calculation for P2, and we'll find, I'm not skipping much here, there's one line that I'm omitting. So P2 is the birth rate again, multiplied by, and now we have the similar sequence of probabilities. There's P1 times P2, and so that is probability that one parent is an AA and the probability that the other parent is an AB, and that happens half the time that will lead to an AB, but we have two different parent configurations, so that gives us a coefficient of 1. And then half of the time when an AB meets an AB, we get an AB out of it. So there's a possibility for AA, AB, BA, and BB. So 2 out of the 4 are going to be the ones that we're interested in for this equation. And then P2, when a P2 is an AB and a BB, and that will be similar coefficient to the 1, 2 term. So that's P2 times P3. And then finally we have when an AA mates with a BB, we're guaranteed to get an AB offspring, and the AA could be mom and the BB dad, or vice versa. So we have 2 possible ways of AAs and BBs mating to get an AB, and that gives us a 2P1, P3. And then we multiply all that by P and divide by P squared, and then minus D2 P2, where D1 and D2 may be different death rates. Okay, so a little subtle to see this, but we can factor this and write this down. Well, when I factor it, I can bring a 2 out in front, and then I have expressions that will be nice for subsequent calculations here. So we have P1 1/2 P2 multiplied by P3 plus 1/2 P2. And if you multiply that through, you'll see you get the same expression as above, but now we have to add in our, oops, that 2 down there shouldn't be a subscript, that should be a superscript. That's squared, and then a P squared, minus D2 P2. And then finally, P3, this one's a little bit easier to write down because we can just take the P1 prime equation, which is this one here, and replace 1s with 3s, and it's basically the same calculation. So we get a P3 squared plus P3 P2 plus 1/4 P2 squared multiplied by P over P squared minus D3 P3. Okay, so a simplifying notation here. I'd like to, instead of keeping track of the total population, I'm not really ultimately going to be interested in capital P, the total population size, but I'm more interested in the frequencies of each of the phenotypes, each of the genotypes. And so I'm going to define those. A is going to be P1 divided by P, and I'm going to rename B P3 divided by P, and I'm going to name the mixed one AB, because that's referred to as a heterozygote. We will call that H, and that's going to be P2, and this time I'm going to divide by 2 times P, which is just a slight deviation, mostly because it makes a lot of the calculations simpler in the sense that they don't have an additional factor of 2 hanging around. But there is also a reason in terms of the individual allele frequencies. All right, so the equations simplify a little bit so far, but not completely yet, down to P1 prime is b, and you can see I can write it as a plus h all squared times p minus d1 p1, and p2 prime, a similar expression, p2p 2b times a plus h b plus h times p minus d2 p2, and p3 prime, which is going to be b times b plus h squared times p minus d3 p3. And now to get the equations for a, b, and h, I'm going to have to use these relationships here. So for example, a equal p1 over p, that becomes, I just multiply through, it's a little easier to do the calculation if I write it like this, and then when I take derivatives, I get p prime a plus pa prime equal p1 prime. And I solve that for a prime, which is what I'm after here, and that gives me p1 prime minus p prime a all divided by p. That's bringing this term over to that side and then divide by that p. Okay, so and now I just have to fill in the pieces. So a prime is equal to p1 prime is this expression above, a plus h all squared times p minus d1 p1 minus, and I'm going to write this as a times p prime, oh well, let's see here. So you'll note, yeah, I'll write it out. So this is a times p prime, and that's all divided by p. But this works out kind of nicely because I get a b a plus h squared, and this p cancels with this p. And then minus d1 p1, but p1 divided by p is just a. And then here I have minus a times p prime over p. And so let's write down what is p prime over p. That's going to be p1 prime plus p2 prime plus p3 prime over p, which is b a plus h squared p. Well, let me just do this on the fly. I can cancel that p with a p in the denominator, so that disappears. And then minus d1 p1 divided by p is a. And then the p2 prime is going to be plus 2 b a plus h b plus h. Now p, but I'm dividing by this p, so that p disappears, minus d2, and now p2 divided by p is p2 divided, oh, so that's going to be 2h. So h here, but then I'll shuffle that over and fit in a 2. And then finally I need my p3 prime divided by p, so that's going to be plus b, big B plus h squared times p, but I'm dividing by p, so it cancels, minus d3. p3 divided by p is b. And so there is my p over p prime expression. And so we can simplify that down a little bit. You'll notice I have a b a plus h squared, b 2b a plus h b plus h, and b plus h squared. So that is very much like, let's say, if we had x plus y all squared, that would give me x squared plus 2xy plus y squared. And so you can see here, this is, well, factoring out the b, so let me get rid of those underlines there, misleading. Oops. So this part, and this part are x squared, 2xy, and y squared. So x is going to be a plus h squared, sorry, a plus a, and y is going to be b plus h. So I can rewrite that part of it as b times a plus h plus b plus h, that's x plus y, all squared. And then minus d1a minus 2d2h minus D3b. But this expression in brackets, that's a plus 2h plus b. And if we look back here at how we defined a, b, and h, when we add them up, that's p1 plus p2 over, so there's a multiple of 2 here, so the 2 cancels from the h, and I get p1 plus p2 plus p3 all over p. And that is exactly 1. So I can rewrite this line as just b minus all of these guys. And so now I can plug that in here into my a prime equation. So I get a prime is equal to b a plus h squared minus, now I'm going to factor out an a, and then I'm going to get d1 plus p over p prime, which is exactly this expression that we just calculated here. So that is b1 minus d1a minus 2d2h minus d3b. And that is the a prime equation. So you can do the same kind of calculation. So let me just move these around a little bit, make some space. So we get b prime by doing the exact type of this exact same type of calculation, and I encourage you to go through that if you want to see how this all works on your own. But we get d3, and this is just really just changing subscripts in a's to b's. So that doesn't need a 1 subscript. There's no 1b or b1. So this is b minus, and this is all the same. And then the h equation is slightly different, but has similar pieces. H prime is b a plus h b plus h minus h, and there's some 2's in there that are going to cancel, so there's a little bit more going on in the calculation here, but just a matter of canceling a few factors on numerator and denominator. Plus b minus d1a, and the rest of it is the same. 2d2h minus d3b. And this is now our system of equations for the genotype frequencies, AA, AB, and BB. And what you can see is that we have the flexibility now to specify D1 and D3 and D2 as different values and see how the system evolves. So I will leave this as a homework exercise, and maybe as for the solutions, post another video going through what happens when you make certain assumptions on those D1, D2, and D3 values.